So ionic compounds, as the name implies, are made up of ions. Specifically, those ions are cations and anions. So you have something that's positively charged and something that's negatively charged. So that makes sense that they should attract each other. More specifically, though, those charges of those ions must cancel out. If there's 1 plus worth of cation, there has to be 1 minus worth of anion. If there's 3 plus a cation, there have to be 3 minus worth of anions in order to cancel out fully. Now, you might recognize that the cations are coming from metals, and the anions are coming from nonmetals, so it's very common to see people say that ionic compounds are made of metals and nonmetals. Now, a couple properties, though, let's go ahead and just get this all out of the way. A couple properties are important about ionic compounds. First of all, they have high melting points. That's because these cations and anions are so attracted to each other, they're very locked in place. That gives them a very high melting point. It's hard to melt these ionic compounds. But because these cations and anions are locked in place, if you disrupt those attractions, it's easy to break them. They're very brittle. Think of like a salt crystal. Striking a salt crystal with a hammer would certainly cause it to break. And then ionic compounds are also conductive, but only whenever they're dissolved or melted. In order for them to be able to conduct that electrical charge, these ions have to have some freedom of motion. When they're a solid, they're locked in place, so they don't have any freedom of motion. But when they're dissolved or melted, they have enough freedom to actually conduct electricity. So let's take a look at how these ionic compounds make themselves, or how they get made, though. This first one is made by combining sodium with chlorine. It helps to think about their dot diagrams here. We know sodium has 1 valence electron. Chlorine has 7. And we often say everything's trying to be like its closest noble gas, so chlorine would only need to gain 1 more electron to be like argon, and sodium would have to lose 1 to be like neon, its closest noble gas. So for that reason, we know that sodium's going to make a 1 plus charge by losing its electron, and sodium's going to make a 1 minus charge by accepting an electron. And this just happens right here with this transfer of this electron from the sodium to the chlorine. Because they're both now satisfied, this 1 plus and this 1 minus, not only, let me start that over, this sodium 1 plus forms a 1 plus charge, obviously, and this chlorine forms a 1 minus charge, and those charges cancel out, producing NaCl. So NaCl would be the formula for the ionic compound formed by sodium and chlorine. If we take another look, here's magnesium, which is right there in the periodic table, and fluorine, which is right there. If we think about the dot diagrams, magnesium has 2 valence electrons. Fluorine, let me try that F again, there we go, has 7 valence electrons. And we can also think about our charges. We know magnesium is going to lose both of those valence electrons, making it a 2 plus charge. And we know fluorine wants to accept 1, getting a 1 minus charge. So we can reason that this magnesium might transfer 1 of its electrons here to fluorine. That would give fluorine his full 8, but magnesium still needs to get rid of this extra electron. Well, there's nowhere for it to go unless you bring in another fluorine atom. So now with the second fluorine atom here, this magnesium is able to transfer its second electron to the second fluorine. If we think about the charges here, magnesium lost 2 electrons, Mg2+. Fluorine each lost 1, so really there's 2 fluorines each with a 1 minus charge. We said earlier that those charges have to cancel. So think, does a 2 plus get canceled out by 2 separate 1 minuses? And the answer to that is yes. So our formula becomes MgF2, where the 2 symbolizes that there are 2 fluorine atoms within this compound. So there's a 1 to 2 ratio, 1 magnesium to every 2 fluorines. Let's try this one. Potassium, located right here, and oxygen, right there. You got a 1 plus. You got a 1 minus, oh, not a 1 minus, my apologies, goodness. A 2 minus, potassium with that 1 valence electron, oxygen with 6, 1, 2, 3, 4, 5, 6. We can see potassium can donate 1 here, But it's similar to the last problem. Potassium was donated his 1 electron, but the oxygen still needs 1 more. So we have to bring in another potassium with 1 more valence electron, and we can see that this potassium can donate its electron to the oxygen. And we now have 2 different potassium 1 pluses and an oxygen with a 2 minus charge. And again, think, do 2 1 pluses get canceled out by a single 2 minus? And the answer is yes. So our formula for this one is K2O. You need 2 potassiums for every 1 oxygen. This one's a little bit different. We got calcium and nitrogen. So we know this is going to form a 2 plus charge. We know nitrogen wants to form a 3 minus. So let's draw calcium with its 2 valence electrons and nitrogen with 5. 1, 2, 3, 4, 5. If we start thinking about how these electrons can be transferred, let's say that calcium donates this first one right there and the second one right there. Well, calcium's satisfied, but nitrogen is not. It needs 1 more electron. If we bring in another calcium with 2 valence electrons, it stands to reason that this calcium can donate 1 electron right here, which would fulfill that nitrogen. But what about this guy right here, this extra electron on this calcium? We need to bring in another nitrogen. Well, this nitrogen's going to have 5 valence electrons. He can accept this one from calcium, which means this calcium is satisfied, but now this nitrogen's missing 2 electrons. Well, you might have predicted it. The solution is to bring in another calcium. Now this electron can go to the second nitrogen. This electron can also go to the second nitrogen. This calcium's lost 2. This calcium's lost 2. This calcium's lost 2. This nitrogen's gained 3. This nitrogen's gained 3. Everyone has done what we'd expected. So if we think about it, we have 3 different calcium 2 pluses and 2 different nitrogen 3 minuses. So let's think, do these charges cancel? Well, do 3 2 pluses get canceled out by 2 3 minuses? Sure. This is a total of 6 pluses. This is a total of 6 minuses, so those are going to cancel each other out, which means the ratio here is 3 calciums for every 2 nitrogens. Now I want to show you a little trick to make this process a little bit easier. If you would just think about the charges that these make, calcium's going to make a 2 plus charge, nitrogen's going to make a 3 minus charge. You can do what I like to call the squiggle method. Bring this charge down and let it be the opposite ion's subscript. Do the same over here. Let this one's charge be the other one's subscript. So this becomes Ca3 from the nitrogen, N2 from the calcium, which of course is the exact same thing we just had here. If we go back through all of our examples, this works every time. We know potassium's going to make a 1 plus charge and oxygen's going to make a 2 minus charge. Just crisscross your charges to become the other one's subscript. So K2O, and then this 1 came down here, but we don't usually write the 1, so it's just K2O, which matches what we said. Same here, we knew magnesium was going to be a 2 plus, and that fluorine was going to be a 1 minus. Just crisscross them. Again, Mg1, you don't usually write the 1, F2. And this works every time. I do want to warn you, though, about let me get some room here. I want to warn you about a certain circumstance. Let's say you had magnesium and oxygen. Well, we know magnesium right here is going to make a 2 plus charge. Oxygen will make a 2 minus. So we have a 2 plus combining with a 2 minus. You don't really want to crisscross them here because that leads you to believe that it's Mg2O2. Well, that's not really acceptable because these ratios here need to be in their smallest possible whole number ratio. So since you can reduce Mg2O2 to MgO, MgO is going to be the proper answer. So if these have the same charges or their charges can end up reducing, make sure that you reduce them down. So it's not foolproof, but it works to find your formula. Well, let's talk about how we name these. So here are the first 4 we did. Sodium and chlorine, magnesium and fluorine, potassium and oxygen, calcium and nitrogen. When you're naming ionic compounds, the cation keeps its name. So the cation keeps name, but the ending of the anion, so the anion ending, changes to "ide." So what that looks like, if we have sodium combining with chlorine, sodium's the cation here, it's going to keep its full name, but we're going to change chlorine to chloride. So if we were going to name this, it would just simply be sodium chloride. On the next one, magnesium is the cation, so it keeps its name, magnesium. Now fluorine, we're going to change this ending to "ide." This is magnesium fluoride. Potassium's the cation. You'll notice the cation always comes first when you're naming these or writing their formulas. Potassium. Oxygen becomes oxide. And our last one, calcium, was the cation, so it goes first, keeps its name. Nitrogen becomes nitride. Calcium nitride.